that. Let me just give a brief intro to Maureen. Maureen's an associate professor here at UWT in the SAM, the Science and Math Division of SIAS, and she earned her MS and PhD in quantitative ecology and resource management at University of Washington. And she works in collaboration with the U.S. Forest Service and the Pacific Northwest Research Station on fire and environmental research applications. And that's all I'm going to say at this point. I'm going to let Maureen talk about her fire modeling work.
All right. Thanks, everybody. Thanks, Cheryl, for this opportunity. And thanks to UWT RRF pilot funding for giving me some space to actually work on the research. It was lots of fun. All right. And so just generally, I want to give you an overview of what it is I'm going to present. And so our objective was to use artificial or simulated landscapes to explore how increasing variability in spatial structure of fuels affects wildfire size and spread. And so I'm going to give a little bit of background about fires, fuels, and space, not space, but space, okay, it's on the ground. A little bit about the simulation system, and then some resulting conclusions and future work. And so I don't think I need to tell anybody who's been around the last few summers around here in the room that fires are an increasing concern throughout the Western United States. This is actually a little bit out of date. You can imagine a few more peaks happening to the right side of the graph. But you see fire area across the US and cost of fighting those fires and resources have been increasing. And particularly, I always find this interesting, it was fairly stable in the late 20th century and this really took off in the 21st century. That fuels is a climate change, probably a little bit of both, but it's a problem, right? And so if we consider what actually affects a wildfire, what makes a wildfire get big, wildfire spread and behavior, fire scientists like to think in triangles. And so this is called the fire behavior triangle, and it's comprised of weather, topography, and fuels. And so weather, we're starting to get a little bit more used to these red flag warnings that you might hear as a weather alert. And so we know if it's really dry, low humidity, if it's really windy, particularly up here, winds coming from the east, if it's really hot, those are the conditions that are really ripe for an extreme wildfire. In particular, fire spread more in the direction of the wind in warm, dry conditions. So topography, that's a terrain. How hilly is it? Is it flat? Are we talking about valleys, mountains, steep slopes, shallow slopes, things like that? And we know that that also affects fire spread more in the uphill direction than in the downhill, for example. And then fuels. So fuels are the things that actually burn up in the fire. So imagine that you're building a campfire. You start with the kindlings, the little bits and pieces, the needles, little twigs, things like that. Then you get to larger logs and branches, and then you can get to entire shrubs, trees, anything that vegetation, biomass that gets burned up in the fire. So the three of these, what do you think we can actually do anything about? Can we change the weather? Not so much. I mean, I can't snap my finger to make it rain right now, right? Can we change the topography? We shouldn't. We don't want to. But what about the fuels, right? I could go out there and remove some fuels from the forest, combust them somewhere else, or make a nice building out of them, right? So I can manipulate the fuels. And so if we think about fire management, particularly in sort of local scales and in the short time frames, fuels are really what can be directly manipulated and managed, that we human beings have sort of more direct control over. And so that's what I'm focusing on, right? Fuels. And so if we are manipulating the fuels, I'm exploring the hypothesis that by those manipulations, we can modify the spatial structure in a way that is more or less conducive to fire spread. That's the sort of hypothesis that I want to look at. And so why am I using simulated fuels instead of just doing these experiments on the ground? And generally, we do these simulation experiments because in the real world, doing the experiment would be very costly, right? So fuel manipulations themselves, they cost a lot. They cost a lot of money, a lot of manpower, a lot of time, right? And a lot of resources. A full experimental design would include spatial structures that result in big fires, right? And so that's a risky proposition. I want to explore. I want to take it to the extreme. What kind of spatial structure creates the worst kinds of conditions? So I don't want to do that in the real world because now I have the worst kinds of conditions, right? So I can do that in the computer, no risk. And then, therefore, you can evaluate extreme conditions and multiple manipulations not possible in the real world, right? So just looking at the full range of potential variability that may not even happen in the real world, but to explore those sort of mechanisms. Okay? So that's why we're going to use simulated fuels. So the simulation system itself is I'm using an eco-hydrological model simulation without fire. So basically, I'm letting a watershed run. So we're talking about tens of thousands of hectare area. I'm letting it run for 60 years without any fire. So the eco-hydrological model, it's a biophysical model, so it includes sort of physical, hydrological, geological processes. It moves water from the atmosphere through the soil, up into plants, down through the groundwater into the stream. Plants photosynthesize according to the temperature, the precipitation, sunlight they get. Therefore, they create fuels in response to those sort of climatic issues, those climatic conditions. And so I'm running that model. So we get monthly simulated spatial maps of fuel loading and fuel moisture across that 60-year simulation. And then I identified maps of basically mean conditions across that 60 years during the fire season. What was like a mean fuel dryness? So a moderate climate condition, and what was a mean fuel loading in that sort of simulation. I'm going to use that as kind of my baseline from which I'm going to start doing the manipulations. And so based on that, I found the sort of mean fuel loading condition for the particular watershed. I guess I should have placed it. The baseline condition, this is the watershed in Sierra Nevada in California, is where this watershed is. So the set mean fuel loading, that happened to be 0.49 kilograms per square meter, which just is what it is. I used the eco-hydrological fuel dryness map, and so I'm not manipulating anything about the fuel dryness, it's just that moderate condition and whatever spatial distribution of that moderate condition that the eco-hydrological model produced. And then from that, I simulated fuel load maps with different spatial structure and different variability. So what that looked like was I created landscapes with spatial structures that were either weak, which means that so it's a pixel, this is great. So there's squares down here, right? So I'm fuel loading here. What fuel loading I am here does not predict my neighbors, the boxes next to me, right? So that's a weak spatial structure. Moderate, maybe I'm 50% correlated, maybe a 0.5 correlation between me and my neighbors. And then strong, all the neighbors look alike, right? In terms of sort of spatial proximity does predict what fuel loading is. Okay. And then I also manipulated variability. So that has to do with the total range of fuels, right? And so spatial structure is given variability, are my neighbors likely to be alike to me? Variability says across this entire room, how alike do all of the squares look? That distinction makes sense? It's an odd distinction, but okay. So then the way I did this is I manipulated variability a little bit more continuously. So this is a factor, weak, moderate, or strong spatial structure. Variability, I took a random draw at plus or minus 25% of that baseline landscape. That mean fuel loading landscape, its variability, its variance was 0.13, no. Yeah, the standard deviation was 0.13 kilograms per meter squared. I did plus or minus 25% of that. And then for each weak, moderate, and strong, I had a range from low variability to high variability in terms of the fuel loading. I used R, the R statistical program, folks are familiar with that, some might be, some might not, to simulate the artificial landscape for fuel loading. I used a spread model that I wrote that actually integrates directly with that eco-hydrological model to simulate wildfire on the artificial landscapes. Is the stochastic model, which means each run is a little bit different, even if the landscapes are the same. So I used 100 replicates for each one. And then I used R again to evaluate the relationship between fire size and fuel variability and spatial structure. So here are some example simulated landscapes. And again, these are extreme examples. So you can see again, this very speckled kind of, oh, the colors aren't quite coming out, some speckled landscapes, right? That's low spatial structure. You have the same fuel variability, say, between these two, but here they tend to clump together under strong spatial structure. Under weak spatial structure, there's no real spatial patterns. It's just completely random. This would be complete spatial randomness. You can kind of see the variability between these two. So the top on both is low variability, and the bottom is high variability. They're all mapped on the same scale from 0 to 1.2. But you can see more dark colors here and more light colors here. And then here, the colors are more in the middle of that spectrum. I think you can see a little bit better here. Lots of big patches of dark colors, right? Whereas the colors are a little more muted. So that's the variability for a given spatial structure. And so what happened? And so here is a graph. So I worked, I worked with Hillary Snelson. I must have taken out for her credit here. So I was able to hire an undergraduate thanks to the funding. So I worked with her over the summer. And so she helped me create these graphs and evaluate these relationships. So here is the increasing variability on the x-axis. On the y-axis, I have median fire size on the top, so the middle of the 100 replicates. 95th percentile fire size on the bottom, so that's the extreme. So I wanted to see not only what the middle condition was, but how extreme do the fires get in terms of these different conditions. And then we have the palest line. These are lowest snooze using ggplot if you're familiar with R, the R universe. So these are just smooths through the points. You can see a ton of variability in the points. This is sort of the trend that those points then summarize. So let's start with the strong spatial structure. And so that's the darkest line there. And so you can see, regardless if we're looking at the 95th percentile or the median fire size, that the more spatial structure you have in the fuels, the clumpier the fuels are, the bigger the fire, right? Because that line's always on top. Right? So if you have the strong contagion in the fuels, you have strong contagion in the fire, and the fire has a place to go, right? But, and I found this to be interesting, there's no relationship with variability. As long as you have that sort of continuity or structure in the fuels, it doesn't matter how much you increase the variability, because the spatial structure itself gives the fire a place to go. With weak spatial structure, if you have very little variability, then it kind of converges to the strong spatial structure, right? Because your neighbor's going to be like you, at least conducive for fire spread, right? Kind of, okay. But if you have weak spatial structure, if you increase the variability, you decrease the fire size. And that effect is more pronounced. You can see this distance is greater in the 95th percentile. So it prevents those extreme fires even more so. So the way I've taken this so far, and this is a preliminary result, is that if you can increase the variability and break up that spatial structure with your fuel manipulations, you should be able to moderate fire spread. Okay. And just here's that example again. Even though there's large patches of low fuels, there's a clear path here that the fire can take. Whereas here, every time it moves a little bit, it encounters something different. So now, oh, here's a high fuel load, oh, here's low fuel load, and it's harder to find a path through the landscape. And so the next steps is I want to change the mean fuel loading, right? So this was a moderate case in both fuel loading and climate. So do these patterns, are they consistent with lower or high fuel loading? Do they change with wetter or drier fuels? So those extreme climate conditions, to that spatial structure. Some people hypothesize that the more extreme the climate conditions, the less any of these other things matter because the fire just blows through everything, right? And so we want to look at that as well. And then do it in the real world, not manipulate fuels, but look at the fuels as they are, find areas or different spatial structures that had fire move through them, and see if we can see some of these same results in the real world. So we're doing this. I have no idea how I did, but thank you.
So we have time for, I think, one quick question, and then we're going to move on. Does anyone have any questions for Maureen? Julia.
Hi, Julia.
Great talk, thank you. I'm just curious, eventually, as you continue your research and move through next steps, how do you hope to apply these this research to sort of the real application?
Yeah,
What would be that?
that's an excellent.
Or
question.
do you aspire to do that?
I do. It's difficult because there really is sort of, we're doing these academic things in the journals, and we're hoping to influence what people do on the ground, but there's always that difficulty moving between them. And so I do work with Forest Service scientists who are closer to the managers, but there's still a little bit of a wall there. But the Forest Service has an increasing interest in more of these landscape scale type of analyses. And so what I hope is that by contributing to our understanding of what happens at that larger scale, that we can translate that through the Forest Service to the managers so that they can sort of take a step back. Because what the managers do, I love these squares, is they say, okay, I'm going to reduce fuels in the square because I know it's going to change fire behavior, and it does, right? But then if you step back a little bit and look across the entire room, which squares should you do that to? Right? And you have your neighbor, you have your forest, you have your national forest right next to DNR lands, right next to the tribal lands, next to people's houses.
Mhm.
And so how do you talk across all of those different kinds of things? And so we start doing these analyses. If we do this basic work, we pull back and do these analyses looking at people actually developing forest plans. And they're really starting to try to collaborate better across all those jurisdictions. And that's where this kind of analysis can really help with that kind of thing. That's the whole thing. Thanks.
Thank you.